Okay, so in this exercise, we want to prove that the operation shuffle preserves the regularity of a pair of regular languages. That is, if we're given a pair of regular languages, L1 and L2, over the alphabet AB, then we want to prove that the language that results from applying the operation shuffle will still be regular. Okay, and so what we actually need to understand first, and the biggest really part of this exercise, is really understanding what shuffle actually does. Okay, so it looks complicated, but trust me, it's not that bad. So shuffle L1, L2, what it does is it takes each string of length, say K, in the language L1, and each string of the same length K in the language L2. And this is for any integer K. And what it does is that it interleaves these two strings together to form a new string where the, the letters of the resulting strings are shuffled between the letters of the string in L1 and the letters of the string in L2. So that is, if I have the string x1 to xk in L1 and the string y1 to yk in L2, where each of these xi's and yi's are letters. Okay, so that's important to remember that these are letters. So they're either A or B, and then these guys are also letters. So they're either A or B. Okay, so for instance, suppose I had A and then B. Okay, so suppose A was in L1 and B was in L2. Okay, then the new string that would occur in the language shuffle L1, L2 would be the string that starts with x1, is then followed by y1, then is followed by x2, then y2, then x3, then y3, and so on. So you shuffle back and forth between a letter from the string in L1 and a letter from the string in L2. Okay, so in our case here, in the case where we had the string AAA and BBB in L2, then the string that we would get out of that would be AB, AB, AB. Okay? So that would be a new string in the language shuffle. Okay? Okay, so that's what the shuffle operation actually does. Now, can we perhaps generalize this to actually look at, say, two languages? So let's say I have the language L1, which contains, let's say, AA and AAA, and I have the language L2, which contains the string B, BB, and then BBB. So what this says is that this says for every integer k, right? So for every length of string in each of the languages, okay, take all the strings with the same length and then shuffle them together, okay? So let's first look at strings of length 1. So there's one string of length 1 in L2, but there are no strings of length 1 in L1, okay? And so you're not going to be shuffling B with any string in L1. If we go to strings of length 2, then we see that BB is in L2 and AA is in L1, okay? And so because the order here matters, because shuffle L1, L2 is different from shuffle L2, L1, let's see what happens when we do shuffle L1, L2, okay? And so you'll just note shuffle is clearly not commutative. Okay? So what is shuffle L1, L2? Well, you take, again, we were at strings of length 2, so you take strings of length 2, in this case, that's only AA, and you shuffle them with the strings of length 2 in L2. So in this case, this is only BB. Okay, so then you would get AA shuffled with BB, so you'd get AB, AB. Okay, then next you would get AAA with BBB, right? Because now you're at strings of length 3. So then strings of length 3, you shuffle the A's, the 3 A's in L1 with the 3 B's in L2. So you get AB, AB, AB. Okay, and then this is the string that would result. Okay. Okay, so that's maybe that. Hopefully that gives you maybe a better idea. So really remember what you're doing is because here the K's are the same. Okay, you're doing this for every possible length, right? That exists in each of the languages, right? So every possible string length that exists in each of the languages, and then for each string length, you're taking all of the strings in L1 and all of the strings in L2 and then shuffling them together. And then you're doing that again for the next available length and so on until the longest string, you would say, in either L1 or L2, right? And the other thing to notice is that sometimes there are strings that don't get shuffled, right? So for instance, here, B doesn't get shuffled with anything in L1, because there aren't any string lengths, right? There aren't any strings in L1 that have a length that match, okay? Okay, so now let's think a bit more abstractly as to how we could prove that this actually preserves regularity. So if I know that L1 is regular, then I know that there's a machine M1, which I'll label as a 5-tuple Q1, sigma, delta 1, Q0, 1, F1. So M1 is a DFA such that the language accepted by M1 is L1. Okay? And then L2 is regular, just means the same thing. So that means that I have some machine M2, which is Q2, sigma, delta 2, Q02, F2, which is another DFA that this time accepts the language L2. Okay, so suppose I have my machine M1 and my machine M2. Okay, so it starts here, it has some final states. This guy also has some final states. Okay, and now let's just pick some K. Okay, so just as an illustration, pick some K. Okay, and now let's consider a string of length K in L1 and a string of length K in L2. So suppose we have X1, X2, X3, Xk in L1, and Y1, Y2, Y3, Yk in L2, right? Again, each of these are letters, so the machine is going to individually read each of these letters, right? Okay, so how does this machine actually do that? For N1, we can imagine perhaps that it reads X1, so it goes to some other state, then it reads X2, goes to some other state, reads X3, goes to some other state, and so on, until it reads Xk, and then it goes to an accept state, right? And then similarly, for the string in L2, length K, perhaps Y1 goes to this state, Y2 goes to this state, Y3 goes to this state, okay, and then Yk goes to an accept state. Okay, so how can we actually create a machine M prime, right? So create a machine M prime that accepts shuffle of L1, L2. Well, what this machine has to do is it needs to simulate the computation of M1 and M2 at the same time, right? So to simulate the computation of x1, xk in M1 and y1 to yk in M2. Why? Because for the string to be in shuffle, the individual strings have to be in L1 and L2. And to ensure that the individual strings are both in L1 and L2, we need to make sure that when you run x1 to xk, it's accepted in M1, and when you run y1 to yk, it's accepted in M2, okay? But now the only thing that's going on, the only thing that's a bit different, right, is that we need to do this at the same time, interleaving the computation step of M1 with the computation step of M2, right? So while interleaving the computational steps, so in other words, the transitions of each machine. Okay, so you're probably thinking, what the heck does that mean, right? So let's do seamless. Okay, so what the heck does interleaving the computational steps of each machine? Each machine. Basically, what I'm saying is that in the machine M prime, right? So suppose this is a machine M prime. Okay. Okay, for the machine M prime needs to process x1, y1, x2, y2, dot, 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 xk, yk. And the x1 to xk and the y1 to yk have to both be in L1 and L2, meaning that they both have to be accepted by M1 and M2 respectively. Okay, so that means that M prime has to actually read through this string. So M prime will read the first x1, right? It will read the first x1, okay? Then, once it does that, it has to switch over and then read the y1, right? Once it does that, it has to switch back, okay, and then read the x2. Once it does that, it has to switch back and remember that this is where it was, okay? Remember that this is where it was, and then read y2, okay? Then again, switch back, okay? Remember that it was at this state when it was reading x2, then read x3. Again, switch back. Remember that it was at this state when it read y2, and then read y3. And so on, right? So it's going to go through this back and forth until it reaches the final states in both its simultaneous simulations, right? So until it reaches this final state from this corresponding machine and this final state from this corresponding machine, okay? And so how do you actually do that? Well, you need to essentially keep track of whether you're reading a string in M1 or M2, okay? And you also need to make sure that you're reading them simultaneously. So to do that, okay, what you can do is you can essentially create states. So you create states of M prime as tuples, okay? So a state becomes a tuple. State becomes a tuple. The last element of the tuple tells you which machine you're in. So either M1 or M2 you're in. Then the first two elements of the tuple, so the first element reads the string, or it simulates the computation of M1, simulates M1, and the second tuple simulates M2, okay? So what I mean by that is at the start, right? So at the start, I begin my computation, right? I begin my computation in the initial states of each machine, right? So I begin my computation in the initial states of my machines M1 and M2, and I start the computation at the machine M1, right? Why the machine M1? Because it's shuffle, right? It's shuffle L1, L2. So the X1 comes first. The X1 is in L1. So I read the string in L1 first, right? And so I need to start simulating the machine M1 first because that machine is the machine that corresponds to L1 because each of these are letters, and the first letter of this bigger string is the first letter of the string in L1. Then I have to start my computation in the machine M1, right? So I start my computation in the machine M1. Now, when I read the letter X1, right, I simulate this step, right? So I simulate M1 reading X1 from the state Q01. And so to do that, I use the transition function that I'm given for M1, which says that if you're at Q01 and you read an X1, you go to some state, okay? And now I'm reading, so I've read the letter X1, okay? I haven't simulated anything for M2 yet, so I'm still at the same state for M2, but now I switch from simulating this guy to going to the other machine and simulating this guy. So to indicate that I've switched machine, I have to do that by indicating that the third element of my tuple tells me that now I'm simulating the machine M2. At that point, I can read the letter Y1. And at this point, right, so now this state doesn't change. Essentially what I've done is I've remembered what the last state I was in the computation of M1, right? I've remembered that. And now I simulate the computation at Q02 reading the letter Y1. So this stays the same, but now I read Y1 from Q02, and now I switch back, right? I switch back to simulating in M1. Okay, and I continue this way, so reading X2, then reading Y2, then reading X3, then reading Y3, and so on until I read XK, right? When I read XK, that means I'm going to the machine M2, right? And then I read the last string in L2, YK, which because I'm in 2 means I'm going back to the machine M1. And now where do I need to be, right? If x1 to xk and y1 to yk were truly strings in L1 and L2, right? If x1 to xk and y1 to yk were truly in L1 and L2, then the simulation of x1 to xk in M1 would have led to a final state in M1, right? Final state. By definition of what it means for a machine to accept, for a machine M1 to accept x1 to xk. And then similarly for M2, right? So this means that the state that I should be here, the state that I should be in M1 should be a final state of the machine M1, right? And then the state that I should be in here should be a final state of the machine M2. So this should be a final state from F1, and then this should be a final state from F2. Okay, and this is what the machine M prime would need to look like, right? Because it would shuffle back and forth between the computation of M1 and M2, and it would only accept the string x1, y1, x2, y2, and so on, if each of the individual strings could lead to a final state. Okay? And so this construction, M prime, is the machine that would accept shuffle L1, L2. The only thing we actually need to do now is to formalize it explicitly. So we only need to formalize explicitly M prime. So if M prime is Q prime, sigma, delta prime, the start state, and F prime, okay, then my new set of states is going to be a three tuple, right? So it's going to be states in Q1 and states in Q2 and this this state that flips between 1 and 2 to indicate whether I'm simulating in 1 or I'm simulating in 2. And so Q prime should be Q1 cross Q2 cross 1, 2. Okay. Then the start state should be, so I should start at the start state of M1 and the start state of M2, and I start my simulation because it's shuffle L1, L2. I start my simulation in the machine M1, right? So if this was shuffle L2, L1, then it would have been Q01, Q02, and then you would have started instead at 2, right? And then you would have gone back and forth. Yeah, okay. And lastly, the set of final states, right? Before I do the transition function, the set of final states is all the final states. So it has to be, you have to be in a final state in the machine M1 and in a final state in the machine M2, and you have to be back in the simulation for 1, right? As I kind of sketched out here, right? Because you go from 1 to 2, then from 2 to 1, and so on. So then if you're simulating xk, then you're going from the machine 1 to the machine 2. Then if you're simulating yk, you're going from 2 to 1. So then you have to end back in the machine M1. Now the most complicated thing to write down is the transition function. So the transition function takes a 3 tuple, Q1, How can I write this? Let's see, let's say P, Q, and then let's say N, okay? And then suppose I'm reading the letter sigma, okay? So based on so exactly what's going to happen, what transition I take is going to be based on whether I'm simulating 1 or 2, right? So if N is equal to 1, so actually I'm going to need more room than that. If N is equal to 1, right, so that means that I'm here, then I keep this element of my tuple the same, right? And I simulate the transition from my machine M1. So this guy is the simulation of the machine M1. So then that's what I'm going to write for the first element of the tuple. I'm going to simulate reading the letter sigma in my machine M1. So from the state P, I'm going to read sigma, okay? Then the state in the machine M2 is going to stay the same. Now all I'm going to do is I'm going to flip to simulating in the machine M2, okay? Right, and so that's if I'm in N equal to 1. Now, if N is equal to 2, then the state in my machine M1 stays the same, but now I simulate using the transition function of M2. I simulate what M2 would be doing if it was at state Q reading the letter sigma. And then I switch back from the simulation of 2 to the simulation of 1. And this is exactly what I've written down here, okay? So this formalization is the explicit construction of the FAM prime that would accept the language shuffle L1, L2. And so I definitely won't dive into the proof of correctness, but if you can convince yourself looking at this sketch and then looking at this simulation that this is indeed doing what it's supposed to do, then the proof of correctness is more tedious than anything else. Okay? All right, and so this completes the solution to this exercise.